And they are the trivial one and non-trivial one from a Z2 class. And in 6 plus 1 dimension, again, we have a Chern-Simons term. We have a gravitational Chern-Simons term, which is 7 form. And but we have 2 of them. So omega 7, d omega 7 is a second Pointryagin class. And the d omega 7 tilt is a square of first Pointryagin class. And both coefficients must be integer. Okay. And so as a result, for bosonic case, we have this table. That 1 plus 1 dimension, we have no invertible topology order. 2 plus 1, we have Z. 3 plus 1, no. 4 plus 1 is here is a Z2. 5 plus 1 did not discuss is no. 6 plus 1 is 2Z. Similarly, for fermionic system, we have this invertible topology order. For 1 plus 1 is Z2, which is this Majorana chain. And for 2 plus 1 is a P plus IP squared. And this is Witten is working on this problem. He claimed that this P plus IP superconductor may be anomalous, may have no UV completion as L-type theory. Again, there's a difference between L-type and H-type. So P plus IP have UV completion as H-type theory, as Hamiltonian theory, but it's anomalous as a path integral. So P plus IP probably is anomalous as L-type theory. So only P plus IP squared is this integer quantum power states is a well-defined fermionic theory of L-type. In higher dimension, we don't know. So actually, this would be really interesting direction. Yes.
Oh, I understand. But so also in the R plus 1 dimension, you can always find it to be 0. Maybe you can have a theory that R plus 1 dimension in the bosonic case.
Yeah.
The invertible.
Yeah, this seems always. I forgot whether it's this odd always 0 or not. Another thing I want to say that on this table, for each dimension we have a group, we have an abelian group. This group also happens to be the cobordism group. And so if you Google cobordism group, orientable cobordism group, you will see this. But the difference is that the cobordism group have is generated by k to 1/3. Cobordism group is a 1/3. So therefore, actually, what I described here is not cobordism group. Although formally it looks like cobordism group. But for the Z class quantization is different. But as a group, they are the same because they're still Z. So for cobordism group, it's E8, not E8Q. And this is also different. The cobordism group, these 2Z are generated by the fractional K1, K2. And here K1, K2 are integer. So they are similar to cobordism group, but not identical. But as a group, but this rational one, this Zn one, Z2 one, that are the same. And so if you check cobordism group, I don't know whether cobordism group for outer dimensional manifold always 0 or not. I forgot. And in higher dimension can be complicated, but I forgot whether they are 0 or not. Okay. So basically that's it. And so this is basically, so I finished the appetizer. So this is topology order and the invertible topology order, and the way we look at this kind of a system, and then we can use in this way of thinking, and the result, and this table will be used later, and this result invertible topology, then we can understand the so-called SPT order, and SPT order are even simpler than this. So we have there we have a kind of complete classification. Okay, thank you.
Okay, now we have time for some questions. Okay.
Yeah, I think for the fermion case, in 6 plus 1D should be at least Z.
Yeah, and I think you're totally right. I think for 6 plus 1D, at least these 2 boson case would I think would exist for fermion case as well.
No, I'm talking about some different. So Well, I think for pure fermion case, it does not correspond in fermion boson case, because 5+1 the wild Mariner fermion has gravitational anomaly and is perturbative.
I see.
So in 6+1 dimensional fermion system should at least be Z.
I see.
Which generates the wild Mariner fermion as 5+1.
Yeah, but what I try to say is that when you have fermion system, you can always stack a boson system to fermion system.
Yeah, that cannot be cancelled.
And
yeah, their relation just like H-like and E.
yeah, I think at least Z2Z, I think, because these 2Z, they both have a local probe. I think they correspond certain kind of generalization thermal Hall conductance. In higher dimension, maybe there's a way to have some two kinds of thermal Hall conductance in some sense, and so I feel at least I think perturbatively the fermion system and the boson system should be similar. They all described by gravitational Chin-Simon term.
Yeah.
So this Z class all correspond to perturbative gravitational anomaly. So I think for boson fermion system, their time should be similar, but quantization may be different. And but for the Z2, they correspond the global gravitational anomaly. So they will be very different.
Yeah, I'm just saying 6+1 the integer quantum Hall.
Yeah.
The integer quantum Hall is stable against any.
Exactly. Yeah, I totally agree with you. Yeah.
And has gravitation not as a boundary. So
Yeah.
that should be.
Yeah.
We expect some pattern will go to higher dimension.
Yeah. And the way I describe this ITO is kind of constructive. And the mathematician want to have a theory which gets this ITO in any dimension in one shot. And so what is this theory which compute this ITO in any dimension? What is theory to compute the cobordism group in any dimension? And there is something like Tom's spectrum or something like that. I just heard the name. I have no idea what they are, and I try to learn them, but it's too difficult. And but there are. I just want to say there is a systematic way to obtain this, and then also there is a systematic way to obtain cobordism group for the non-orientable manifold, for manifold with a spin structure and all that, and there is some conjecture that if you study the cobordism group on manifold with spin structure, may get a classification fermionic system, which I don't know, should I believe that or not believe that? And the reason is that in condensed matter physics, the fermions are not Dirac fermions. You know, the fermions do not satisfy Dirac equation. The spin structure corresponds to Dirac equation. So if in the field theory fermion are Dirac fermion, so spin structure is very natural. In condensed matter, the fermion just a fermion. There's no spin, and no Dirac equation. And so why fermion system should be related to spin structure is not obvious. In field theory, they are obvious, but condensed matter fermion are not field theory fermion. So I don't know. So there are issues.
Yeah, I have a question. In the middle of the talk, you mentioned about the some ZSD equals to 1, right? So that means the ground state degeneracy on a SD sphere should
Yeah.
be 1. So I'm thinking, is that related to the fact that any fiber bundle over a SD manifold should be trivial? So is this related to that fact?
Yeah, probably.
So
There should be a good way to understand this. Just I haven't been. Yeah, the mapping class group is kind of trivial.
yeah, so
Yeah.
actually.
This comment is important in the following way. If you look at the mathematical literature, the simplest topological quantum field theory are defined in 1+1 dimension. And organic condensed matter physics, in 1+1 dimension, there is no topological order. So then why mathematicians study 1+1 dimensional topological quantum field theory, which should correspond to topological order? The answer is no. They actually, the mathematicians study symmetry breaking states. So they all correspond to this is not equal to 1. So in 1 plus 1D, the topological order theory is not equal to 1. So they're kind of unstable. So they correspond to symmetry breaking states.
Next question.
I was also asking a question about the staking. Like,
Could you speak louder?
like, my question is about staking.
Yeah.
Like, take 2 ground states and take the tensor product of these. Is this the staking operation?
Yes.
But then I don't understand why this is a different way because it's just a tensor product of 2.
Yeah.
Well,
But each ground state is not 1. So for first system, you have a ground state labeled by alpha. Second system, ground state labeled by beta. When stacking psi alpha and phi beta, you get a ground state labeled by alpha and beta. So the number of ground state states is a product of a 2.
but to me, I still don't think that this is just another.
Okay, let me write it down.
So
So the
I totally understand what you mean, but I just don't understand why you treat this as a.
so that is so this is for system A. This is for system B. Then that is this whole thing is for system A plus B, and that's it.
Yeah. That's also how I understand.
Yeah, so you can see the ground state is increase. You never go back to 1. So therefore it's so therefore usually if a ground state is not equal to 1, they have no inverse.
Okay.
And because they are gapped, so any small interaction are irrelevant. So they flow to 0. So consider non-interacting stacking will be enough. Yeah, that's a stability of the topological order against any perturbation. Yeah, that's a so.
All right. So let's thank the speaker again.